Mr. Amal. In case of a warehouse building having connected load more than 100 kilowatt, and without air conditioning, is it possible to model the building in eQuest? Is there any ways to switch off air conditioning options in eQuest? Warehouse buildings are not coming under industrial. Has somebody now the question first of all is okay. I'll take the first half of the question a bit later on, but let's take the second half of the question. Warehouse buildings. Why would it? I mean, has there been any specific notification or anything telling that it is not exempted? I'm asking all of you. Anybody can probably answer. So is there any specific notification which has come at warehouse?
Industrial building only not mentioned in the ECBC code, but the storage building also included.
Let me take out that ECBC. Hang on. I'm sharing my screen. Give me a minute. Right. Yeah. All right. Let's look at this. What does this say? Can you read this? 2.1a. Building envelopes except for unconditioned storage spaces or warehouses. So that's your answer. How can you say that warehouses are applicable?
Perishable warehouses standard.
Except for unconditioned storage house spaces or warehouses. Warehouses are clearly not applicable.
For unconditioned only, but perishable goods storage is included.
Or warehouses, that will, I think that will, I mean, cold storages, if you see, I don't think it would not come under, it will not, building envelope will definitely not come under, you know. That's my take. Of course, the authority having jurisdiction, that means the Kerala municipality has to take a call, but clearly, you know, that's quite frankly, why is this code made for? This is made for people, you know, where there is, we have to understand the basis of the code. This is for people, not for perishable goods or anything else. This is for people, where people are staying, only those buildings. So basically, I would say regularly occupied spaces would be more apt in this case. So I don't think this should be, you know.
Sir, yesterday they mentioned storage building also included for a conditional area.
I think you have to that clarification has to be sought from again authority having jurisdiction. They should either the EMC, someone should clearly tell that. I personally feel it should not.
EMC staff also here. No, they can answer.
Yeah, I mean, you can take a decision collectively, but ultimately EMC will have to come out and communicate it to the municipality and panchayat that whether ECBC will be applicable on cold storage spaces or not. So that's the job of EMC, I would say. Ultimately, they have to communicate.
Okay.
Just by discussion, nothing will happen. It has to be in black and white. Until unless you have in black and white, I mean, that's a exception, I would say. Now, equipment and portions of building that use energy primarily for manufacturing process. Okay, that's different. Provided, however, offices, godowns, or buildings of any other purpose other than manufacturing in a manufacturing facility that having a connected load of 100 kilowatt and greater or contract demand of 120 kVA and greater or having conditioned area of this. So yeah, if we look at this part, this is actually, you know, there is a conflict between this one and this one. So it may not necessarily be manufacturing, it may be storage also. They have to include the storage also. So it can be a conditioned storage space, for example, a cold storage. The cold storage has its own design requirements. The entire HVAC requirements are completely different for cold storages. Their design is completely different because they are dealing with mostly sensible load and of course a bit of latent load. So in my opinion, this has to be taken up by EMC. They have to come up with a clarification and communicate it to the authority having jurisdiction, which in our case in Kerala is municipality and panchayat, and municipal corporations also, of course. So the first part of the question, how do we model anything without HVAC? So let's look at that. All you have to do is, let's say this space is unconditioned. Okay, all you have to do is change it to unit ventilator. All right, and then you look at this. See, this is how it comes. There's just a supply fan, and you can zero out the supply fan power. You know, here you can actually zero out. Oops. Oh, I'm sorry. That's restore default. Yeah, there you go. You can literally zero out this one. All right. The cooling and heating tab will be all, you know, you can change this to not installed. That should be okay. And also make sure that in the zones, you remove these thermostat schedules. This should be removed. If it is an unconditioned zone, there should be no thermostat schedules in the zone. Okay, just like in plenum, they have this NA. Similarly, in over here, this should be thermostat schedules should be undefined, but the zone type should be conditioned. Please remember. Yeah, you can either use some or you can use unit ventilator. Either one is fine. You can also use some. That's also perfectly fine. Okay, just make sure even if it is some, one of the space needs to be conditioned, right? Otherwise, you will get an error. So, a very good question of point. I mean, very good way of pointing out. So there are, you have an ultimate goal. There are at least 4 or 5 ways in which you can that goal. So you can say this is correct, this is correct. The multiple pathways are correct. At the end, the common goal should be achieved. So Mr. Basil, I will take up your question a bit later on. You'll have to change your settings, and if you did not delete the INI file, then it can lead to errors. So please make sure that you delete the INI file, configuration file. So can we not define as unconditioned space? At least one of these spaces needs to be conditioned, even if it is a zone under sum or unit ventilator. You have to have one. Others you can keep it as unconditioned, that's fine. But the moment you change this, you remove the thermostat schedules, it automatically becomes unconditioned. That means nothing is, it will no longer try to fulfill the temperatures over there. Okay, so thermostat schedules is basically the temperature of that zone, what the system will try to achieve for that zone. Okay, the moment you remove the thermostat schedules, it kind of becomes an unconditioned space. It is nothing will, I mean, the system will no longer try to fulfill the temperatures because there's nothing mentioned over here. Yeah, even if it is unconditioned, that's fine. Or did you, so all these zones need to be connected. All these zones in the model need to be connected in air side, even if it is unconditioned. I'm sorry, could you rephrase that? All the zones in the model need to be connected in air side. I am not sure what you mean by connected in air side. Or do you mean conditioned? I think you mean conditioned. Yeah. So to show you, let's say I do this unconditioned, all right? Now this is also unconditioned. Both the spaces are unconditioned. Now look at what error I'll get. Oh, it completed successfully. Oh, okay. Maybe this one is sum. Okay. This is sum, so maybe that's why no error. Ideally, what we practice is just keep one of them as condition. Okay. Okay. So sum is okay, but the moment if I change it to, let's say, unit ventilator, I think we will get an error. For some, you can keep it unconditional. Yeah, there you go. So if it is sum, then okay, terminated due to. So if you open this, I think that error will show up. There you go. System EL1 sys1 GS2 has no condition zone. One is required. So anything apart from sum needs to have one condition zone. Okay, so if I change this to, let's say, sum, I think it should be fine. So again, you can do trial and error, and you can always find out this. Unless you do trial and error, you can rectify. Yeah, so for some you don't need a condition zone, right? I hope that makes it clear. So let's look at simulation output and let's try to understand what we have in the detailed simulation output file. Right. So the first and foremost thing, if I look at BPS or BPU report, is that I have a lot of throttling range, right? 2368. So first and foremost, I need to find out where I'm getting that throttling range. So for that, I'll go to SSR, right? And the number of undercooled or unheated hours are being shown over here. And you can switch the systems. And let's, okay, so you have 156 here, GC7, that's fine. 13, 16, 22, 6, and 385. So TC21, you can probably take a note. What I'm going to do is take a note here. TC21 is one which has 385 hours. Okay, so GW4 has got 581, GC5 579. I think all of these. TS11 346, 301. So anything what I'm looking at is basically anything greater than 300. I'm looking at all those zones. TN13 643. Okay, so TW14. So this is where a huge number of throttling range is coming in, and this is the 2361 TC15. Okay, so there you go. Right, so let me try and address the biggest one first, which is TC15. How would I address it? I'll then go to SVA. I'll look at this TC15. Now what I can see is the floor area is 3074 square feet, right? 3074. And the CFM that I see is 884. So if I divide 884 divided by 3074, I'm getting 0.28 CFM per square feet, which is practically speaking very low. Ideally, it should be somewhere around, the minimum I would say should be 1 CFM per square feet, but sometimes in auto size, because what Equest does is it auto sizes, which means that it will calculate its load and it will calculate the system. So let's first see where the TC15 is. TC15, that's the one, yeah. Okay, so this is definitely a big space, and as you can see, you have a very big space, and then yeah, a big roof. Okay, so good question, Mr. Azim. When system is auto-spicing, why do we have unmet hours? Ideally, not everything is perfect. We are not living in a perfect world. So even though it is trying to, but you see, what happens is the system is being designed at design conditions. So design conditions are not given here, but design conditions, the temperature and relative humidity will be different. Okay, that is why if you see the schedule here of internal loads and external loads, see occupancy schedule, day schedule, week schedule. Okay, you have this heating design day and cooling design day. So cooling design day is weekday. Okay, so here I think we have not specified the design day, but it will automatically from the weather determine its own design day. So that design day is not equivalent to peak. Please remember, the design day is not equivalent to peak. So for a design day, it has determined its own load, but when the simulation runs for the entire year, that design load is not being encountered. It may be encountering completely different loads during the run through the entire year. So that is why, even though system is being auto-sized, it is being done for a particular 1 hour, 1 or 2 hours throughout the year. It is not taking into consideration the entire 8760 hours. So that is why there might be mismatch. Okay, so in fact, what we can see now, what we see over here is that 29.931 is the system auto-sized capacity. Let's look at the peak load for this specific space TC15. So that we can see from I think summary of spaces. Oops, not summary. Let's go to details of spaces. Yeah, here the details. There should be building loads, building monthly space, monthly load components, space peak load components. Yeah, let's go to this one, and let's go to TC15. Okay, so here, as you can see, the total load for a design condition on April 21, 4 p.m. it is being determined as 7.542 kBtu per hour. Our system was designed for 29 kBtu per hour. Right? What is the difference? Now, what happens is, because there is a huge roof surface. Now, please understand, there is a huge roof surface on this. So this is the space. So throughout the day, heat is being added into this small space, and the heat keeps getting added on. So this is just 7.542 is just for 1 hour, which is at 4 p.m. But what is happening in reality is, right from the day, so east, the sun comes and it starts, 12 o'clock, 1 o'clock, and there's also temperature outside. The temperature of this space starts increasing significantly. And that is something, again, which you can see. So LSB is space peak load components. Then you can also correlate this with space temperature summary. For TC15, there you go. You can see the space is consistently above 80 degrees Fahrenheit. In fact, above 75 most of the time. So which clearly indicates that the air conditioning system is not fully capable, even though it is sized for the peak load. But when it can remove only our sizing, you see, is 29 kBtu, as we saw, TC15, 29 kBtu. So cooling capacity is 29 kBtu per hour. So every hour it can remove only 29. But imagine that from the morning itself, almost 10 kBtu keeps getting added, and first hour 10 kBtu it handles well because peak is this. But then what is happening is, as you go later towards the day and towards the night, that heat is being added up, and it is significantly greater than what this cooling coil or capacity can handle. Right? So that is one of the key things to notice when you are trying to find out what is going wrong. Okay, you have to understand how air conditioning works. The air conditioning is what it is doing is it is only removing the heat that is coming into the space. So I hope you understood why, when even if the system is on auto size, we have unmet hours, right? So apart from minimum design flow, the other things that you can do is basically increase the cooling capacity of the coil, or try to see, for the envelope, because roof is the major component. Okay, let's say now what I'm going to do is add a parametric run here. Tools, parametric runs. I'm going to suggest high SRI paint. So what I'll do is, this is on construction, clear all. On the roof, I'll apply a high SRI paint. So basically I'm decreasing the absorptance. Okay. Now let's simulate both of these. So to the question, can we directly enter a higher cooling capacity for base case when system is auto sized? Ideally, you cannot enter it directly. You have to increase it. I'm going to show in a short while. Okay, set none. Let's look at this first. Okay, and let's go to SSR and PC15. Let's see how much of a difference it made. So 2361, and now it is coming to 2336. Okay, so so that means there are other things which are happening, and one of the main things that is happening is, as I said, there's pent up heat. The amount of heat that is being stored is insufficient. So the best way is to actually increase the cooling capacity or the flow rates, and it would automatically result in a higher cooling capacity, right? So let's take for an example, this was the TC15. What I'm going to do is, in this zone, the minimum, I'm going to increase it. In fact, I'm going to put it here. Let's say 1. Okay, and I'm going to change this to 1. Right? So let's see the baseline. Let's just see the baseline and see what happens to the cooling capacity. Remember earlier the cooling capacity was 29. You see, straight away a dip of more than 1,000 hours. And let's look at SVA. PC15, as you can see, the cooling capacity has automatically increased. The moment you increase the flow rates, the cooling capacity automatically increases. Now floor area, this 3074, I think this is the total of, I don't think. Let's look at TC15. Or was it TC15? Yeah, TC15. Okay, this is the core space. All right, okay. So its area is 1537, right? So the area that you see here, oops, this is for the entire, that includes conditioned and unconditioned zones. All right. So our actual area was 1537 for just for the space. Okay. And now 1537, if I'm correct, 1537. So 1768 divided by 1537, in fact. So it's coming to about 1.15 CFM per square feet. So that's a start. You know, I can probably take it up to 1.5 or maybe 2. 2 is will be like maxed out. Ideally, it should not be greater than 2. Okay. So what are the other things that we can do? Maybe provide ceiling insulation. Let's look at the ceiling, or we can also go for wall insulation. You know, in baseline case, because it will be stringent, you would in any case have to give insulation in the baseline case. So ideally these should not happen. Oops, sorry. Let's look at wall construction. It is already, you have insulation over here. Let's look at roof construction. Okay, there's good amount of insulation. Okay, probably the reverse might also happen, because there is so much, it's such a small space. It could happen that everything is just packed in, the heat gets trapped, there's no way for it to escape. So if you give more insulation, sometimes that might be counterproductive. That can also happen. So you have to really strike a balance. Even a higher insulation, what will happen is, you give in higher insulation, sometimes the heat that is generated within the space itself can't get out, and that increases the space temperature, and as a result of that, the unmet hours will also get increased, right? Let's see, what is this high wall construction? Okay, just a U value input. All right. So let's see if we reduce the amount of insulation, would it help? Okay, what I'm going to do is, in the layers roof construction, I'm going to reduce the amount of insulation. I'll put it as 0.1. Let's see what happens now to that same space. Okay, so from 0.25 feet of thickness, I reduced the insulation to 0.1. Let's look at this same space. Go to SSR, TC15, 1218. I think it reduced a little bit more. Okay. So as you can see, sometimes the in fact, let me note it down. Let's just check it. 1218 was in SSR, TC15, 1218. Let me revert this back to 0.25, and let's see what was the number of hours out of throttling range. 1231. Okay, so you can see clearly we gave more insulation, but all it was doing was probably trapping heat. Yeah, and we can probably also check for overall. It gives 1484. Let's reduce the insulation and see what happens on the overall. 0.1. So it was 1484. Let me note that down. 1484 before change, and after change, let's see what happens. One 1484, 1492. Really not much of an impact, you see. So it's very likely that other zones also you can. It's just the air conditioning system which is not designed or which is inadequate, I would say. So if you increase the flow rate, it is very likely that it will be all right. So as you can see, probably TC21. In fact, we had so many spaces at the earlier one. TC21, 376. Okay, 549. GW4. Earlier it was 581. 547. A slight drop, you see, a slight drop in everything. This is TW14. Okay, I did not write TW14. I think, no, yeah, 1801 hours. So it has dropped to 1366 hours. So most of these would be because of inadequate flow. So the moment I start correcting the other flows also, it will have an impact on the adjacent space also. So let's look at some of the last ones. I'll focus on 13, 14, and 15. Okay, so this is 11, this is 12, 14, 13. So if we look at 3D geometry, I think this will be part of oops. This is 15, TW15. TN20. Okay. I'm sure, am I looking at the correct one? Okay, sorry, it was EL2. This one. EL2 is this one. Okay, so 11, 12, 13, 14, and 15. So 13, 14, and 15. And where are these? I think these will be the most exposed ones. And yeah, because you see, you have this glass also, this window 30. Okay, which I told would be like an atrium. So a lot of heat is coming in through this, right? So I would say, you know, and this is 11, this is 12, 14. So, and where is this? This is 13. So most of the heat is coming from 14 and 15. Now, one of the things that we can do is, you know, why did the roof did not have such an impact? Because we had glass on top. Okay, so maybe if we reduce the SHGC, translation dome 1, let me change it to 0.25, and let's see the impact now. There you go, 259. Straight away, you see the design was wrong because we had so much of glass. That's why we were getting such high throttling range. The moment I changed the glass, it was automatically fixed. And let's also see for TC14. I'm sure this would have also dropped down. So you see there was so much of heat that was coming in from here. Let me in fact change back to 0.66, whichever was the earlier one. 0.66, right? Yeah. So 0.66. I think we saw the wrong TC15 when we are looking at the loads. So it is impacting the nearby adjacent spaces also. Let's look at loads once again. Space peak load. Go to summary or components. TL2 core space. Okay, yeah. I think we looked at the correct one. Yeah, that's fine. So it is. I'm not sure why this is not taking window. No. TL2 core space TC15. I'm sure that is the one. Yeah. Okay. Yeah. TC15. And let's look at core plenum. This is where most of the heat. So what is happening is most of the heat that is coming in the sealing zone, it is being transferred into the zone below. I hope you are able to understand. That is why I said, these indirect transfers are difficult to figure out if you put in sealing zones. So it's always easier to figure out if you have a single core zone, right? So that is how you have to kind of assess and kind of find out where the problem lies. There will always be a problem somewhere. You have to just figure out, think logically as to where the loads are coming and where is it going. Okay, so let's say I switch this back to 0.25. So you can see this has decreased almost by half the total load in the plenum zone, peak load in fact. Go to SSR. In fact, let's see the summary BPU. It is 609 now, right? So there may be a couple of more spaces where there will be an issue because of undersize of the air conditioning system. Okay, TC21 still remains. GW4, GW5 still remain. TW14 remains and TC15 has dropped. So let's look at TW14, which has 423 unmet hours. I'll go to SVA, TW14. So supply CFM is 1426. Floor area will be probably half of this because this includes plenum zone. So 2983.5 divided by 2, 1491 and 1426. It's almost giving 1 CFM per square feet. So that's approximately right. So let's this is TC 14 or TW 14. Okay, which is the west wall, I think. Okay, so you have shade, so some amount of shading should do. But let's look at the glass properties. In fact, the glass is window type 2. Type 2, the parameters are not known. Okay, so this is a library entry. The parameters are not known, but we can still find out what the SHGC and other things from the detailed output report. So for that, what we'll do is we go to details of exterior spaces, and here you can see window U value. You can find out, okay, the SHGC is not here. Let's see, there must be something for the windows. Yeah, details of windows. Yeah, frame value. Okay, the shading coefficient. Yeah, shading coefficient is here. Okay, so we are looking, the main concern for us is the shading coefficient. So let's look at which glass it was. Okay, EL2 West Twin TW14 E12W1. E12. Is this the one? EL2, no. TW14 E12.W1. Yep, this is the glass. Okay, so we had glass shading coefficient. This is the effective shading coefficient, which is coming out to be 0.57. Right, so maybe we can probably use another glass and with a lower SHGC. So if I create a glass, glass type simplified, shading coefficient, I'll say 0.3, right? And this is okay, glass conductance is okay. And just for this one, I'll change the glass type to glass type 6. And let's see what the impact is now. Okay, this one, the shading coefficient reduced to 0.30. Let's look at the loads. 302. There's a slight reduction. I think earlier it was 400 something, 464. Now it has come down to 302. So that is how you can actually use different options for the proposed case most of the time. In base case, it's very likely everything will be under control if you have modeled everything correctly. One of the things that you could look out for is, as I said, this one, airflow. You could actually increase it to about 1.5. Let's say if I put it as 1.5, it should ideally satisfy. Yeah, as you can see, the throttling range has come down, and it is at 492. So probably a couple of zones would be left. So as you can see, some of the major ones have reduced it. So it's almost very likely the case of undersizing. You can go up to about 2 CFM, and most of your throttling range should get controlled in that. If you put as 2 CFM, ideally you shouldn't do it, for everything, all the systems. Maybe 1 or 2 systems you could do it. That's perfectly okay. Sometimes it happens because the software is not perfect. So that's perfectly allowable legally as per the code. There's nothing barring you to do that. But in proposed case, you really cannot model whatever is given in the data sheet has to be followed. So for example, 441, you cannot increase this flow. In the base case, because it is auto-sized, yes, you can increase the flow, but definitely and definitely not in the proposed case. For the proposed case, you'll have to probably tell the client to slightly oversize or change the system. For example, this is rated cooling capacity is 1 ton, this 12,000 BTU. Maybe tell them to put another 7,200 or half a ton. So that way you can increase the airflow rate, the CFM in that space. So that can be, those are the recommendations that you can give, apart from upgrading the wall and roof. Sometimes that might not be feasible because putting insulation into the wall can be a bit tricky. So in that case, the air conditioning system has to be upgraded by putting in one more AC. So those are things that you can do. Ultimately, it has to result in savings. Okay, I hope that gives a little bit of clarity of how you can reduce throttling range and give you an overview of how to interpret the results of what you get here. Okay, just give me 1 minute. Yeah. So other errors that you can actually make while you are doing something is the schedules. Make sure that before you even run the simulation, you are absolutely 100% sure about the schedules. That is, occupancy schedule, when is it starting? So for example, in this case, it is starting at 7 o'clock. Okay, almost 70% occupancy is starting. Let's look at the HVAC and fan schedule. So fan schedule, weekday, it is starting at 7. Great. Let's look at cooling weekday, is starting at 7. So all of that matches. Now look what will happen if I just change this to Instead of the cooling schedule, if I make this 0 and this starts at, let's say, 11 o'clock, see what will happen to my throttling range. The number of hours, unmet hours, will increase significantly. Okay, earlier we had 400 something unmet hours. You see it increased to 1345, right? All because we had a mismatch between when the fan is in operation. When does it start? It starts at 11 o'clock, but as per our set point is 76. So when the fan is off, that means there's no supply. There's no supply air. So even if your cooling coil is on, doesn't matter. There's no supply air going into the space. So be very careful when even a slight mismatch here will end up causing throttling range. So I just changed that back to 1 again to start at 7. And there you go, drop down to 492. Okay, is it possible to estimate energy demand for totally unconditioned building considering natural ventilation effect alone? You can do manual calculation if you want. Yeah, you can do, just if it is a naturally conditioned building, just technically it is sum. Okay, just put it as sum or maybe unit ventilator and zero out the fan energy, and that's it. You should have everything. I mean, the energy consumption for your lights and equipment would still be there. So that is what you have to calculate. You can either calculate it manually by hand, or you can just calculate using eQuest. Either one is fine. No, wind flow effect is not considered in eQuest. Natural ventilation, it cannot give you any answer. Whether you will achieve thermal comfort or not, that cannot be determined in eQuest. And if we look at the code, let's look at HVAC for a moment. Does it say? Yeah. So if it is naturally ventilated, you just have to comply with this part. Natural ventilation shall comply with the design guidelines provided for natural ventilation in NBC 2005, Part 8, Section 1 --. So just look up these two sections, and from NBC, just make sure that it is being considered, and that's it. You don't have to prove anything else. How can you compare? There's nothing left to compare because there's ideally no air conditioning. So you can just you can comply with this natural ventilation, and then everything else is applicable. So just put in base case, proposed case, and here in eQuest you can just take it as sum or maybe unit ventilator, whatever suits you, and you'll get the energy consumption and you can compare. So basic comparison would be between lights only. The lights will be the only thing left out for comparison and nothing else in a naturally ventilated building, because there's nothing else you have to enter over here. See, building shell doesn't matter because air conditioning we are not even looking at it, because thermal comfort is not a criteria here. So you just have to ensure you meet these U value requirements, which are again prescriptive requirements. They are not mandatory. So ideally, you can just get away with, quite frankly, underperforming envelope also. So thermal comfort, other softwares are, yes, Design Builder or Energy Plus. You can say Open Studio Energy Plus, they can provide. And of course, you have IES software also. IES and Design Builder are paid software, while Open Studio with Energy Plus, basically both are linked. They are free software. So in that you can find out the thermal comfort in detailed output reports. That's that. Okay, let's see what else. Yeah. Okay, so let's look at some other errors which you might encounter. Suppose you are making some changes and you put this system, the parent system. Okay, let's leave this for the third one. Let's say you change the parent system. Okay, and this is the space type is, package single zone with a control zone, which is over here. Now I save this. The moment I open it, I'll get an error. What kind of error is for everyone to look now? Okay, so this says must be attached to system to be specified as its control zone. So whichever is the control zone, that zone must be in the, and of course there's no conditioned zone in this. So here you can see EL1 west perimeter W03 must be attached to system W3 to be specified as its control zone. And here it says the system has no conditioned zone, one is required. So it clearly means I have to shift this one to this. That's option number 1. Option number 2 is to actually put this also under W1 and delete this system entirely. So those are the two systems using which I can eliminate the error. Okay. So an unconditioned zone, it can be anywhere, it doesn't matter, the parent system does not matter, but to be a control zone, it should be here. Okay, W3, because the control zone for system W3 is space W3 or thermal zone W3, right? Okay, let's understand a bit more about the reports also. How can you find window to wall ratio? So that comes under details of exterior surfaces. Scroll down, keep scrolling down until you find a page something like this, where it gives northeast, southwest, and roof, the average U values, the window area, and the wall area, and window plus wall area. So for each orientation, you can get these values. So window area divided by window plus wall area will give you the window to wall ratio of that orientation. And if you want for the whole building, take the all walls. Don't take walls plus roof. All right. Next, let's look at Psf report. So for different meters, you can actually find out the month-wise usage and the maximum kilowatt for that month and the peak end use. Okay, you can choose the meter from top here. You can have multiple meters, and overall here you can see the peak. So this peak end use, it depends on your schedule. So on your schedule, if you have let's say throughout the day the peak is 70%, this will be 70% of the peak. So let's say this is for lights. The first one is for lights. Let's look at the schedule, the weekday schedule of lights. Oops, press in your lighting. Yeah, there you go. So 0.9 was the highest. Okay. So actual kilowatt would be this divided by 0.9. Now this is only giving the peak. So that is 90%. You can see over here 0.9 is the highest among all of these. So the moment if I do this as 1, you see it will increase. So it was 32.478. Let me revise that. And as you can see, it has hit 36.087. Okay, that's something that you can always try and check. Ideally, whatever you have on the lighting drawings, when you sum up all the kilowatt, it should sum up. The total should sum up. This kilowatt should match, right? And of course, the schedule should remain the same. I'll change this to 0.9. If I simulate this, there you go. Okay. So that's that. Now let me make a chiller based system. Okay, where I'll connect some of the spaces to chiller. So for that, I'll create a chiller here. I'll make it electric screw and chilled water loop, starting points, default CSW, condenser type. I'll make it water cooled. Library CW is condenser water. Done. No. Okay, that's a problem with eQuest where it crashes if you make a chiller. Go project 34. Let me change this to variable air volume, library, default CSW. Okay, done. Right. So now if we make a chiller, it will automatically get attached. Chiller type, screw. Okay, chilled water loop, condenser type, water cooled, done. Default CW. Okay, done. Yeah, and let me put a cooling tower, which is heat rejection, open tower. Yeah, there you go. Right. Let's put some more systems into this. Change this to variable air volume, default, maybe the bigger one, variable air volume. Okay. Air volume and default. All right. Okay, so let's simulate this. Now remember, the chiller is an auto size. So if you want to know what is the chiller size or chiller capacity, come to PSD, okay, circulation loop loads, and here you can find the default CSW. Sum is 430.9, okay, MBTU. Seems a bit high, but it is what it is. Or yeah, this is the one. Okay, so 430 MBTU, that's the load. So you can convert that into tonnage. So 430.9 divided by 0.012. No, 1 ton is 0.012 MBTU. Yep, that's a bit high. Sum is MBTU. Sorry, I'm sorry. This 198.6, but even this is high. I'm not very sure why it's so high. Let's look at PVA. Yeah. Okay, you have to go to PVA. Here you will get the rated capacity. Right. I'm sorry. Yeah. So you have to go to PVA, not PST. Okay, so here you will get the cooling capacity of default CSW, which is 0.26 MBTU per hour, 0.26 MBTU per hour. You can see both even under circulation loop and even under the chiller. Don't take the capacity of condenser water. Condenser water capacity will always be greater than chilled water capacity. So when we define tonnage, we define it only for the rated capacity, okay, for the chilled water loop. So 260,000 per 12,000, that's 21 tons. Okay, that is how under PVA, plant design parameters, you will get the chiller capacity. Now one more thing you have to also remember is that when manufacturers give you the EER, energy efficiency ratio, or COP, or whatever is defined over here in KS ECBC, so these, these COP, please note that these are under standard test conditions and not design conditions. The COP at design conditions, by design conditions I mean for a location like Kerala, would probably be less than what is defined over here. So because the test standard, it considers the outdoor air, I think at 35 degrees Celsius or so. So that's the test standard, but in reality, in practicality, your design condition will be probably 40 or maybe 42. Okay, so please remember, when you're asking for a test certificate or COP or anything, or even when you are vetting a tender document, please ensure to ask or make sure it is written that at ARI test conditions. The COP is at ARI test conditions and not design conditions. Okay, please remember that very well, and that goes on for even if you have VRF, although VRF is not given over here. For VRF systems, you could refer to ECBC 2017, I think, the national ECBC 2017, although there's nothing given over here. Okay, so that's one thing that you have to remember very well. Okay, yeah, that is basically what I can think of from my end. Anything else, if you would want me to, I'm here the few minutes, and you can always take up questions. The floor is open. You can sit for another 15-20 minutes if you want, or half an hour. But yeah, if you have any doubts, please write it down. Any other things that I have missed? Any questions, please?
Sir, can we ask something other than equals, sir?
Yeah, yes. Anything, general, anything. Yeah, please.
Okay, sir. Suppose a shopping mall which is intended to be designed as an air-conditioned building. Can we do a calculation with? Can we show a calculation with artificial ventilation?
With an
air-conditioned building is already designed as an air-conditioned building.
It's already designed as an air-conditioned building, correct?
Building. Yes, we don't have natural ventilation. So, is there any possibility that we can change it to a artificially ventilated like that?
Naturally ventilated.
With mechanical ventilation, whether we can do like we can convert that into a mechanically ventilated like.
If it is, I think if it is already designed as an air-conditioned building, it will be very tough to convert it into a naturally ventilated building.
Okay.
It'll be very tough because you see, if you want to make it naturally ventilated, that means you should create sufficient pressure differences. Okay, so there should be an you should be able to study from which direction wind is coming, and then you should have suitable openings which will allow. You see, what happens is if you put in, you remember the Jali mechanism that we have in our older tradition jalis, grills with jalis.
Yeah. Yes.
So the very reason why they had those small openings was to create that pressure difference. What happens is when the air passes through that small opening, the pressure drops, and the moment the pressure drops, it gets cooled. The air gets cooled. So approximate 2 to 3 degrees, it was getting cooled, and it was also aiding the velocity. So that is the main function of that jali. So creating that pressure difference. So, and then you need to have an inlet and of course an outlet also. So you have to study that wind pattern, and during the peak, when you have high humidity, that's when you require high velocity of air. Only then you can satisfy the thermal comfort. So quite frankly, those are the specific reasons why it will be very difficult to convert it into a naturally ventilated building, because it is already designed as an air conditioned building.
Not naturally ventilated, sir. Some sort of mechanical ductable ventilation sort of things. Can we introduce like that? Like that, can we change?
Mechanical ventilation, if you do, the size of the fans required will be very high. You can do mechanical ventilation, yes, no doubt about that. But you have to remember, I'm not sure. Let me just see NBC. Give me 1 minute. I just want to show one graph to you. Let me see if I can find that graph actually. So thermal comfort is a function of your wind velocity and also the relative humidity. It's just not temperature. So you really need to have something which measures the relative humidity of the incoming air or outdoor ambient, and then what is the speed at which you are throwing in, that mechanical ventilation is throwing in the air. So that velocity has to be varied as per the temperature and relative humidity. So in that case, yes, it can be done if you have that good amount of control, but again your fan size is going to increase definitely.
How we will justify this to the not to the customer? How we will justify to the department? So this comfort can be attained. How we can really justify?
But why would you want to change that? You see,
To reduce the cost of, to reduce the energy cost.
I mean, is it a government department or is it a
Yes,
private
yes.
client?
Actually, it's for Devasam board. It's an Annadanam hall. Called the hall is purely dedicated to free supply of food. Dining. It's a dining space actually. Common dining space. Actually, it's not.
Oh, okay. It's a small dining space, you're saying.
It's not a small dining space. It's a big dining space with the integrated kitchen facility and all.
The food court.
Multiple floors.
Food court. Food court in shopping mall.
No, not a shopping. It's a religious building.
Religious building.
Yes, yes.
Yeah, I think you can put in like how big is the space?
It's huge actually. It's around 30 meter by 70 meter like that.
70 by 70, right?
30 meter by 70 meter.
30 meters by 70 meters. 2100, 21,000 square feet. Is it on ground floor, first floor, like
4 floors? 4
sorry,
floors. 4 floors. Total 4 floors.
Oh, total 4 floors. And similar area.
Yes, also almost.
So if you totally want to remove air conditioning, if the just the top floor, you can increase the height of the entire room. So instead of standard 10 feet, you might have to go for maybe 15-20 feet, and then not 15, sorry, you will have to go to 20 feet, just the double. And of course, introduce ventilation fans, which should be sufficient to cater to, you know, the conditions, inside conditions. The thermal comfort can be achieved without air conditioning, but you definitely need to put in ventilation fans, number of ventilation and exhaust fans. Does that make it clear?
So that calculation we need to provide to the department for the air volume change calculation.
Yeah, I think I'm just going to show. Give me 1 minute. You can use the NBC. That's the best way. NBC 2005 gives it. I think 2016 they removed it for some reason. I don't know what. I don't want to officially speak on that here. Just me. Got it. The question SLD using Nanocard. Okay. Okay, yeah, I'll get that to you. 1 minute. So this is what recommended values for ventilation. Maybe you can use this chart, air changes per hour. Okay, and this is the chart that I was talking about. Table 9, desirable wind speeds for thermal comfort conditions. So based on the drivable temperature and the relative humidity, you have the velocity. These are the velocities which you need to make sure that it is provided within the space. So that simple calculation you would have to do. Even just acceptable is fine, you know, you can use these conditions. So because just acceptable, it goes up to 36 degrees Celsius, and 40 we don't encounter 90% relative humidity. But yes, with, I mean, even if you the internal space, if it's a dining space, if you have a high wall, obviously you can reduce the temperature itself to about 34 degrees, and then at 80%, if you ensure this 3.05 meter per second, this is really high, but if you can ensure this with air changes, you'll have to calculate, you know. So this is the speed and then amount of volume of air that you want to change. You can do this calculation. So the formula is velocity into area gives you the volume, right? So you can find out, just use the formula Q equal to V into A, and then how many fans you have, air changes per hour. So that's the volume of air that you want to change. Okay, air changes per hour. So from that you can actually calculate. You'll have to find out how much the with this velocity, you know, let's say 3 meter per second, yeah, 3 meter per second. With that velocity, what is the area that you have for extraction. Okay, so you multiply the meter per second by the square meter, you will get meter cube per second. And how much the fan can extract. Okay, so you have slots, you will have slots for the fan, so that is your area. From there, the velocity you want is 3 meter per second. Okay, so you will get exactly the quantity of air that can be removed. I hope you are understanding. If I draw this in a plan view, from a front view, let's say, let me go to Nanocard here. Let's say you have this as the wall. This is your wall, consider. Okay, you are seeing from front, and you have for exhaust fan, let's say, this window where you will always obviously have to put in a mechanical ventilation. And let's say this, oops, I'll just copy this, sorry. Let's say you have these four. So the area for this is 1.1539, whatever it may be, millimeter square, or maybe if you want, you can call it square feet, 1.5 square meters, let's say. So you have 4. So multiply this area in square meters by 3 meter per second. Okay, so you will get meter cubed per second. So that's your flow volume that you want. So accordingly, you have to select that ventilation fan, and you will get, the quantity of air, the volume of the room you already know. Okay, so you will get the desirable things. Okay, can you demonstrate? I hope that answers the question.
So an expert in HVAC design can do this.
Yeah, the HVAC designer can do it. Yeah, all these concepts. But ideally, my recommendation is that you have to at least increase the height. Without increasing the height, you really cannot provide the heat. And of course, you need to provide excellent ventilation fan.
Okay.
Sir, I had a doubt. Sir, this CMH calculation, can you please repeat, sir?
Sorry?
Actually, the CMH calculation, this cubic meter per hour. So the ACH we can get from the manual, the NDC manual. The standard ACH is defined, whether it is a warehouse or whatever we can select from the table. And as you mentioned, the cubic meter per hour, that the room volume has to be taken, or the opening volume we have to take, which we have to take.
No. This is the volume of air that will flow through that opening. Okay, but you still need to fulfill this condition. Air changes per hour. That also needs to be fulfilled, because you have to maintain that O2 also, oxygen. So you have the entire volume of air. So let's say I want air changes per hour. Let's say my volume of the I have 10 by 10, room of 10 meters by 10 meters, and height 10 meters. Oh, not
Okay,
10 meters.
Room volume I have to take. Okay.
So 300. So 3 into 10 into 10. So 300 cubic meter is my volume, right? So that 300 cubic meter, if I want to change it for 8 times, so I have 2400 cubic meter that I have to ensure that every hour that gets out. Okay, plus I have my own requirement from the opening. I say that, let's say this is 1.5 square meter, okay, into 4. So 1.5 into 4, and let's say 4 walls, okay, into 3 meter per second. So 72 cubic meter per second my exhaust fans can handle. Sorry, 72 is what my present state is. Okay, so 1.5 per window, that is the area of the opening. 4 number of windows, 4 walls. Okay, so this is my opening area times 3 meter per second is the velocity that I want, right? So if I multiply that, I get 72 cubic meter per second. This is the minimum that is required, cubic meter per second. Please note this is cubic meter per second. Okay, whereas this 2400.
Sorry to interrupt. This room volume, if I get say 300 meter cube, the room volume. So that air has to be displaced through this exhaust fan ducts, right? There will be fresh air fan also. So suppose there are 4 fresh air fans and 4 exhaust fans. So this the same volume is displaced through this fresh air will sit there and exhaust will pull it out. So is there any we can take the room volume alone, right? That will be correct.
So that's where I'm saying, see, if you want to ensure, you see this is 72 cubic meter per second. If I multiply it by 60, you need at least 4320 cubic meter per second. This is only 2400. So your exhaust fans must be designed to cater to, exhaust and supply fans should be designed to cater to 4320 cubic meter per hour. Did you get my point? For minimum fresh air, you need 2400 cubic meter per hour. But to ensure thermal comfort, we need 4320 cubic meter per hour.
Okay, including the openings.
Yeah, including the openings. So your exhaust and supply, ultimately, whatever amount of openings or whatever, if you want your, either way, what I'm saying is your fans should be able to displace 4320. You can do it from 4 openings, 2 openings, 10 openings, doesn't matter. But at the end of the day, 4320 should be catered. That's what you need to
then we have to divide this by the selected fan CMH, available CMH. Then we will get the number of fans.
Exactly.
Okay, so that number will be a combination of exhaust and fresh air, right?
Sorry?
If I say I got if I selected a fan with a particular CMH, I divided this value with that. So I got 8 numbers. So the 8 numbers, can I say that 4 plus 4, 4 exhaust and 4 fresh air? Or I have to put 8 plus 8?
No. You have to put 8 plus 8.
Fine. 8 plus 8 mechanical fans. Okay, fine. If I do ducting, the case will change.
Yeah, that's also fine. You can do ducting. That's also fine. You just have to take into account the duct friction losses. That's it.
Okay. Losses also we have to add to this. Okay, fine.
Yeah.
And also the height, I have one question. This height, discarding the false ceiling, we have to take, right? Up to false ceiling. There is false ceiling in the space.
Yeah. Yes, you could do that. That's a good way. But I would suggest, the higher the room, the lower will be the temperature. But of course, you can have a lower false ceiling and then, equivalent height of, that way your mechanical volume will be less. The volume of the.
We can reduce the energy requirement also. Okay, fine.
Yeah.
Sir, if I put any timers or any controls for these fans, then we have to add any allowance to this CMH, which we calculated, is 4,320. If I am having an energy management system or any timers for this energy efficient operation of these fans. So suppose I am putting VFD or something. So
Right. Yes.
will that be affecting this value?
Yes, absolutely. What you can do, I would say, is connect it to a CO2 sensor, so which will detect the number of people. If there are less people, you can save energy. Put VFD on the fans also accordingly.
Okay, so during design stage, this value, we have to select the maximum value.
Yeah.
Okay.
Just
okay.
give me 1 second. 1 second. Yeah, sorry. Sorry. Please go ahead. Somebody wanted to ask any question?
Okay, thank you, sir, for that clearing that doubt. Because initially I had worked for a commercial kitchen. Their exhaust is a very important thing. Bulk cooking was there. So that time this code was not there. ECBC code was not there.
Right.
Now, yeah, that's why I suddenly got this doubt. Thank you, sir.
Right. Okay. Got it. Give me 1 second. I'm going to address the questions in the chat. Yeah. Okay. Let me take the first one. Can you demonstrate making SLD from CAD file using Nanocard? Yes, I can. Let me see if I have something. Okay. So let's say this is an area. I'm in the model view. Yeah. Okay. So all I have to do is, go to layer, make a new layer. I'll call that SLD. Make that as the current layer, maybe change the thickness of this to 0.25 or maybe even more. I know where I'm going. And then that's it, really. There you go. You can keep making these SLDs. Line weight is not visible in this case, so yeah, and so on. Okay, I'm not going to go very deep into it, but that's your SLD layer. Okay, and then you can mark the windows wherever you want. Oops. Okay, I hope you are able to follow that. You can continue in this fashion. So this Nanocard, just import it and draw over it, and then you can just switch off all the other layers. Or you can in fact lock the other layers. a lot of layers here, and then only the SLD. You can keep it unlocked. Okay, and that way you can actually copy whatever you have drawn into a new file. There you go. Okay, so that's how you can create the SLD and then copy it into a new file and save it as a DXL. Okay, so that's a very quick way that I was demonstrating as an example for making the SLD from CAD in Nanocard. If we have a building where which has 100 kV, no air conditioned space, there might have different machinery. How can we model the building? Is how we consider the loads, load should be considering in such a building. If there's no air conditioned space, then I don't know. Or if there are any spaces which are regularly occupied, probably for that you might have to show the what should I say? Thermal comfort maybe, and otherwise, you know, for the equipment as was clarified earlier, you know, for the equipment that is electrical power, some motors, you need to still comply with the code. With the lighting, you need to comply. Just the air conditioning, maybe nothing much over there. The building envelope, maybe nothing much over there, but all these other things you'll have to comply with. And of course, if there is equipment and portions that use energy primarily for manufacturing processes, of course, that are also exempted from the code. And if you are asking how do you want to exactly model that, just go to direct loads over here and put it in over here. Either interior direct loads, yeah, put it under interior direct loads, so that will reflect in miscellaneous. Or you can just put it on exterior and then change the end use to miscellaneous equipment. So that's one of the way. The next question is here. Let's go to table 11.2. Let's go. Okay, so we have 7-floor building, built up area 3000 square meter. Can we use VRF for base case model? No, we cannot. That's the clear cut answer, because you have to go for this. This falls under this category. 7 floors. Clearly, you have to go for central plant in the base case, which is chilled water plant. So you cannot model VRF. That's for Mr. Philip. When we add interior load, we also need to define schedule. Yes, we do need to define schedule. Yes, without schedule, nothing will get operational. So let's say lighting, this is an internal load. You have to have defined schedule. If you don't define schedule, this will not be considered. I'm sorry, I cannot understand you.
The previous case, the area is, though the floor number of floors is more, the area is only 3000 square meters.
That does not matter. You know, the rule is a rule. It's clearly mentioned. If it's more than 5 floors or more than 15,000 square meters, either one of these, then you have to, you know, go for centralized pooling. And in any case, the centralized pooling will give you more energy consumption. So the proposed case, you will in any case be achieving savings. So why are you even worried? Okay, so
Constant volume.
sorry, could you repeat? Okay, are there any other queries? If not, I think constant volume, can we take package system? Constant volume, like it can be any I mean, are you talking about proposed case or base case or what exactly?
Base case.
Base case, all right. One second. Constant when we take package system, that depends. For example, your first one, PTAC, I think except the last one, everything else is constant volume. But for residential, you'll have to have package terminal AC. For less than 3/4, package single zone. Okay, so only for those two cases can you take packaged system. The other two cases, you can take package system. You will have to go for chilled water based system. Although what it says is that the first one of the one with chilled water, it says it should be constant volume. Okay, so the fan will be constant volume. Okay, so can we call it a day?
Hello participants, do you have any doubt, any further queries?
Maybe in real life we can do that, but as a part of the evaluation, we have found some buildings with a very poor envelope performance. So that the capacity.
Hello Azim, are you talking? Are you asking any doubt?
Am I audible?
You are not clearly audible. Can you please speak a bit louder?
Hello, am I audible now?
Yes.
Yeah, much better. Yeah.
Hello.
Yeah, please go on. Yeah.
Uh, so my doubt is actually as part of the evaluation, we have found that when we are evaluating a building with a poor envelope, the capacity, air conditioner capacity requirement is quite high. But the already designed air conditioner provided capacity was inadequate, and we had, when we tried to model, that was giving much unmet hours. Actually, if we are auto-sizing, this would have been taken care partially, but since the capacity was already decided, that was not being met. So in that case, actually, in that case, we could not proceed with the evaluation. So what is your call on that?
Tell the client,
Because
I mean, the air conditioning, you have to tell the air conditioning design team to look into the parameters they have done to design the, because they take these U values into account. If the U value is wrong, then obviously the load calculation will be wrong.
Okay.
So you have to tell the HVAC consultant to redo that calculation and inform the client if you feel that your calculations are correct.
Okay. And actually, one of the greatest challenges in this is, even for the base case, for getting the under 300 unmet hours for all the 4 orientations.
No, I don't think it is required for all the 4 orientations. It's just for the one single orientation that you require.
Don't we need to meet that for all the 4 orientations?
No, it's just the one orientation, one single orientation.
Only for that we need to check unmet hours.
Yes, the actual orientation should be under 300.
For the other orientations, we only take the energy performance. We don't look at the unmet hours.
Correct.
Okay. Maybe that's a relief actually.
Yeah, it's clearly mentioned. I mean, it does in the code. It clearly says that.
Okay.
It doesn't talk about all the 4 orientations.
Okay. Thank you very much.
Yeah. Welcome.
Dear participants, we will send you the link for the feedback form. Kindly fill it and send us back. I think we can wind up the session, sir.
Yeah,
Participants,
think so.
I think there are no further doubts.
Actually, yesterday there was some request for sharing the videos for the 2 days. Is it being done?
We can do that in next week. Actually, its video is under processing. We will send it in next week.
Okay. Thank you.
Okay.
All right. Thank you so much.
Okay, thank you, sir. On my personal behalf and also on behalf of EEB Cell and EMC Kerala, I express my heartfelt gratitude towards you. Thank you, sir, and thank you, participants.
Great. Okay. Everybody have a great evening, great night. See you sometime later again.
Thank you, sir. Same to you.
All right.